All right, welcome to the AI Research Roundup. I am your host, Alex. Today, we're looking at a paper that's been getting a lot of attention on Papers with Code. It's called RWKV-7 Goose with Expressive Dynamic State Evolution. This paper, published March 30th, 2025, presents a new model architecture that's really efficient. It has constant memory usage and inference time per token. It introduces a generalized delta rule, which is a fundamental learning mechanism that helps the model adjust its internal knowledge. Achieving new state-of-the-art results on multilingual tasks with a surprisingly small model. So for anyone who wants to dive into the code, the implementation for this work is part of a larger library on GitHub called Flash Linear Attention. It's a collection of highly efficient implementations for what are called linear attention models. Linear attention is a more efficient way for an AI to decide which parts of the input are most important, allowing it to scale to much longer texts without slowing down as much. You'll find all the code, benchmarks, and usage examples right there in the repository. Okay, so to really see what makes RWKV-7 a step forward, this table gives us a great comparison with other recent architectures. It's looking at different types of recurrent neural networks, which are models that process text sequentially by maintaining an internal state or memory. The table compares them on 4 key properties, like having a large complex memory and a dynamic way of deciding what to remember based on new words. If you look down the list at models like Mamba or RetNet, you'll see they each have some of these advanced features. But the key takeaway is at the bottom. The new RWKV-7 model is the only one shown here that successfully combines all 4. This unique combination is what gives it such expressive and dynamic capabilities. Alright, and here in Figure 1 we can see the architecture that actually makes all of that possible. On the left is the overall model structure. Information starts at the bottom in an embedding layer, which converts words into numerical vectors and flows up through a stack of identical processing blocks. The real innovation is the green time mix module. On the right, we see a close-up. This module is how the model remembers things. It takes its memory from the previous step and uses the new WKV-7 kernel to update it with information from the current word. This updated state is then passed on, creating that dynamic memory we talked about. So, after seeing the high-level diagram, this figure gives us a closer look at the actual math inside that time mix module. This is essentially the formula for how the model's memory, represented by these colored grids, gets updated. The new state on the left is calculated by taking the previous state and then applying this complex set of operations based on the current word. This calculation is a visual representation of the generalized delta rule, a sophisticated process that lets the model dynamically blend old memories with new insights. And keep in mind, the figure uses small 4x4 grids to keep it simple. The actual state is much larger. Alright, so for a model with such a sophisticated internal logic to actually work well, you need to train it on an enormous amount of data. This table gives us a sense of that scale. It shows the total number of tokens, which are basically pieces of words, used to train the different RWKV-7 models. You can see the training was done in stages, using different versions of a dataset called World. If you look at the largest models, the 1.5 and 2.9 billion parameter versions, they were trained on a staggering 5.6 trillion tokens in total. That massive multilingual dataset is what allows the model to develop its strong capabilities across many different languages. Okay, so, after all that training on trillions of tokens, this is where we see the payoff. These charts compare the performance of RWKV-7 in red against other models on multilingual benchmarks. The chart on the left plots accuracy against training flops, which are basically a measure of the total computation used to train the model. You can see that for any given amount of compute, the RWKV-7 models achieve higher accuracy. Then, the chart on the right tells a similar story for inference. It compares accuracy to active parameters, which relates to how much work the model does to generate a response. Here too, RWKV-7 delivers better accuracy for a similar computational cost. This shows its superior efficiency in both training and inference. Now, after seeing its strong performance across many languages, this next figure gives us a very similar view, but this time focusing specifically on English language benchmarks. The charts are set up just like before, with training efficiency on the left and inference efficiency on the right. And the story is just as positive. The red line, representing the RWKV-7 model, shows that it achieves performance right on par with other leading models of a similar size. This is great to see. It confirms that the model's efficient and powerful design translates effectively to strong results in English as well. To wrap things up, what we've seen with the RWKV-7 model is a really compelling alternative to the standard transformer architecture. It delivers top-tier performance on par with other leading models, but with the massive efficiency benefits of a recurrent neural network. This research is a powerful reminder that there's still so much room for innovation in core model design. That's all for this week's AI Research Roundup. Thanks for tuning in. I'm your host, Alex.